Welcome back, students. In this video segment, we will look at one section, section 3.4, sum and difference formulas. In this section and in the next section, we're going to learn a whole bunch of new identities for the course. In fact, we're gonna concentrate on most of the remaining identities for the rest of the course, and there are quite a few of them. So what I would suggest you do is, if you haven't already, open, and if you can print it out, that would be great, but at least have open, if possible, the handout posted on Canvas that I just posted on Canvas entitled Identities. And on that handout, you're going to see most of the identities for the entire course. Okay, and I'm going to be referring to that handout as I go through this lecture. Okay, so if you don't have it open now, or if you don't have a copy of it now, you might want to stop the video and either print out or open the file, have it available to you if possible. Okay, so I'm going to start out with a true or false question that I always start this section on. True or false? The sine of 30 plus 60 degrees equals the sine of 30 degrees plus the sine of 60 degrees. And I'm going to let the cat out of the bag right away. This is absolutely false. This is absolutely false. There are very few functions. There are very few functions that you can distribute into sums or differences. In fact, for all practical purposes, it never works for functions. It's a very common mistake to say that this is true, or to manipulate the trig functions this way, because we train you with the distributive property very early in algebra. But this is not multiplication. This is a function, sine. We're evaluating a function at 30 degrees plus 60 degrees, and it does not, just like almost every function, it does not distribute inside of sums and differences. Okay, it's easy to check that this doesn't work. You can work the left-hand side and the right-hand side separately. The left-hand side would result in, if I added 30 and 60, I would get 90, and the sine of 90 is 1. That should be known to you by now. On the other side, we compute the sine of 30 is 1/2, plus the sine of 60 is radical 3 over 2, and we get 1 plus radical 3 over 2. And these are not equal. 1 does not equal 1 plus the square root of 3 over 2. So it's really easy to see that this is false. It turns out, though, in STEM field math, and specifically for calculus, which is where most students who take trig are headed, we need to be able to somehow disrupt 30 and 60 degrees in some sort of fashion without adding the 30 and 60 degrees together. For example, if I'm dealing with the sine of, say, theta plus 60 degrees, I might want to simplify, or not simplify, but I might want to expand the expression sine of theta plus 60 degrees, so that I'm dealing with trig functions of the individual angles theta and 60 degrees. In other words, I'd like to be able to do something close to, if possible, distributing the trig function through. Well, that's what the first of our new identities is going to allow us to do. So back to the identity sheet. On the first side, it's a two-sided, I guess since it's on Canvas, it's 2 pages. It's a 2-page handout. On the first page, you're going to see listed the identities that we've learned so far. So we're about halfway through the course, and it took us half a semester to get through the first page of this identity sheet. Well, there's some bad news. There's a second page to this sheet and this handout, and while it took us half a semester to learn and use the first page of identities, we're going to go through the second page in 2 meetings, in 2 lectures. Okay, so there's a lot of work for us to do. That's the bad news. The good news is, if you learn these identities the way I'm going to try to suggest you learn them, it won't be that difficult. There are patterns to these identities that are very easy to memorize. So if you instead of memorize each identity cold as an individual item. You memorize the patterns that are formed by these identities. I think you'll be able to do this in the short amount of time that we're going to need to do this in. So in this video segment, we're going to address on the second page, we're going to address the first 6 identities. They're called sum and difference formulas. In the next lecture, set for section 3.5, we will study the remainder of the identities. We'll do the double angle formulas, power reducing formulas, etc. on that page. So let's go ahead and get started. I would like an identity that allows me to work with the sine of the sum of 2 angles without adding the 2 angles together. And that's our first identity. The formula on the second page of that identity sheet, the formula for sine of alpha plus beta is the sine of alpha. So it looks like it's distributing, but not quite. It's sine of alpha times the cosine of beta minus the cosine of alpha times the sine of beta. Okay, and we simply memorize this formula, although I did make a mistake in the formula. The sign in the between is plus, and after that's real embarrassing for me because this is my 31st year of teaching this course here, and that's a big mistake. So the formula for the sine of alpha plus beta is sine of alpha times cosine of beta plus cosine of alpha times sine of beta. Okay, so there's another formula. Our next formula is for the difference of 2 angles, the sine of alpha minus beta. And here's where my statement about the memorization of patterns comes in. The pattern for the sine of the difference is very similar. The sine of alpha minus beta is the sine of alpha times the cosine of beta minus the cosine of alpha times the sine of beta. Okay, so it has sort of a nice, easy flowing pattern. If you look at the right side of each of these identities, it's sine, cosine, cosine, sine, sine, cosine, cosine, sine, sine, cosine, cosine, sine. Okay, and then further, it's alpha, then beta, then alpha, then beta, alpha, beta, alpha, and beta. Okay, and the formula between sine alpha and cosine beta and cosine alpha and sine beta is the same sign that's on the left-hand side. So the pattern is sine, cosine, cosine, sine, and with the variables alpha, beta, and the signs stay the same. The signs stay the same. So for the sine of alpha minus beta, it's sine alpha cosine beta, same sign minus cosine alpha sine beta. In any case, you ought to memorize these formulas. In fact, all of the formulas from both sides of these pages. You'll need to memorize them for calculus and stuff. So let's take a look at working with these identities. So for example, find the exact value of, let's say, the sine of 15 degrees. Find the exact value of the sine of 15 degrees. Now, there's a common mistake. I'm going to bring this up. It's wrong to do this. It's a fairly common mistake. It's wrong to say, well, the sine of 15, well, here, let's do it this way. The sine of 30, we memorize, is 1/2. We know that. So the sine of 15, since 30 is half of 15, 15 is half of 30, should be 1/4. No, it doesn't work that way. No, no, no. Okay, absolutely not. Absolutely not. Now here's the explanation of that. The sine of 30 is 1/2, and you can certainly multiply both sides by 1/2. We teach you that in algebra. You can take equations that are true, and you can multiply, add things to both sides. You can multiply both sides by 1/2, and it is true that 1/2 times the sine of 30 is 1/4. But there's no way that that 1/2 is going to get past the sine. You can't take constant multiples of trig functions, take the constants into the angles. There's nothing you can do with this last expression. You cannot bring that 1/2 and multiply it by the 30 degrees. Okay, so what do we do? A trick here, the trick here, or a trick, because there are a couple tricks you could use. The trick here is to take 15 degrees and make it into either the sum or difference of two angles that we're familiar with. Angles that we use commonly, like 30 degrees, 45, 60, and 90 degrees. So 15, can you think of 15 as something minus something, some angle minus some angle, where each of those angles that we find are common angles? Well, if you didn't get it, what's 45 minus what is 15? 45 minus 30 is 15, and we know how to deal with 45 and 30 degrees in terms of the trig functions. So what I'm going to do is I'm going to use one of the trig identities, and specifically I'm going to use the one for the difference to help us deal with this problem. So I'm going to write right above this. I'm going to write, oops, not there. I'm going to write right above our problem the formula for the sine of alpha minus beta. It's, oops, that's a second time I made a mistake with that. It's the sine alpha cosine beta times cosine beta minus cosine alpha times sine of beta. Remember, this is multiplication separating the two trig functions, and separating the two terms is subtraction. Okay, so now let's apply this to the sine of 45 minus 30, with alpha's playing the role of 45 degrees, and beta's playing the role of 30 degrees. Okay, let's thicken that pen a little bit. Okay, so going to the right hand side, then alpha's 45, so this is sine of alpha, sine of 45 degrees, times cosine of beta, beta's 30, minus cosine of alpha, alpha's still 45, and beta's 30, so sine of 30. And then we know these trig values through unit circle or the chart of special values or just sheer memorization. By now, this should be real familiar numbers. Sine of 45, radical 2 over 2. Cosine 30 is radical 3 over 2. Cosine of 45 is radical 2 over 2, 45 degrees, and the sine of 30 degrees is 1/2. So now comes our experience with algebra and radicals. Radical 2 times radical 3 is radical 6. Radical 2 times 1 is radical 2, with the same denominator of 4. And that's the exact value of the sine of 15 degrees. It's not a real practical problem in the sciences, because very rarely do we need an exact value of things like the sine of 15 degrees. But it teaches us how to use these formulas, okay, without doing too complicated of examples. So there was a first example. Suppose I'm interested in a second example. Find the exact value of, let's say, the cosine of, let's see, pi over 12. Okay. I want to do the same thing as I did in this last example with sine, except I want to do it with the cosine function. And I want to do this with radians. So I don't want to convert to degrees. I don't think it's a good idea for you to convert from radians to degrees. You should stick in radians to get used to radians, because they are the angle of choice in ways. They are the way of measuring angles in calculus and physics formulas and stuff. So I want to find the exact value of cosine using a sum or difference formula. That means I need some more identities. So moving on with our identity list, I have a formula for the cosine of alpha plus beta and alpha minus beta, so we'll do that separately. It shares with the formula for cosine of alpha minus beta a similar pattern, but the pattern is not the same as for sine. The pattern for the cosine is cosine, cosine, sine, sine. The pattern for the angles alpha beta still holds, so it's cosine alpha, cosine beta, sine alpha, sine beta, and the sign changes from the left-hand side to the right-hand side. So if it's plus on the left, it's minus on the right. So if it's minus on the left, it's plus on the right. And the pattern is cosine, cosine, sine, sine, cosine, cosine, sine, sine. And the sign in the middle changes. So back to the original two formulas, the patterns for the sine identities. The pattern was sine, cosine, cosine, sine. And the sign in between stays the same as it was on the left. With the angles alpha, beta, the pattern alpha, beta. For the cosine, it's cosine, cosine, sine, sine, so it's a different pattern. The alpha and beta pattern stays the same. It's cosine alpha, it's alpha, beta, and the signs between the cosines and the sines terms change from the left-hand side to the right-hand side being opposite. So the left-hand side is cosine alpha plus beta. It's going to be minus, separating the terms on the right-hand side. Okay, so off to our example, the cosine of pi over 12. I want the exact value of the cosine of pi over 12. This one's a little trickier for students generally. I want to write pi over 12 as something minus something, where each of the somethings are common angles for us. I could choose 5 pi over 12 minus 4 pi over 12. And 4 pi over 12 reduces to pi over 3, which is pretty good, but the 5 pi over 12 doesn't really cut it. So instead, I'm going to use 4 pi over 12 minus 3 pi over 12. Both of those reduce to angles that we're familiar with. Okay, so the cosine of pi over 12 is cosine of 4 pi over 12 minus 3 pi over 12, or the cosine of pi over 3 minus pi over 4. And I think I'll scoot that over a little bit, and then maybe if my surface won't act up too much, there, I'll just move it. Let's do this right about there. Guess I could have just rewritten it, huh? So alpha and beta are playing the roles of pi over 3, and I'm sorry, pi over 3 and pi over 4 are playing the roles of alpha and beta. So alpha is pi over 3, cosine alpha, beta is pi over 4, cosine beta. Change the sign from minus on the left to plus on the right, and then sine of pi over 3 and sine of pi over 4. Okay, and each of these numbers we're familiar with. We've been working with them all semester long. The cosine of pi over 3 is 1/2. And the cosine of pi over 4 is radical 2 over 2. The sine of pi over 3 is radical 3 over 2. And the sine of pi over 4 is radical 2 over 2. So using our radicals from algebra, 1 times radical 2 is radical 2, radical 3 times radical 2 is radical 6, common denominator in these fractional expressions is 4. So radical 2 plus radical 6 over 4. That's the exact value of the cosine of pi over 12. Okay. So let's take a look at one more example. And that will end this video segment. Let's take a look at one more example. Yeah, the video segment's going to be pretty short today. Okay, a lot of work to do in homework, but as usual. But the video segment's short. So here's the setup for the example. We're given some information about two separate angles. We're given that the cosine of an angle alpha is 5/13. And we're given that alpha is between pi over 2 and pi. And we're also given some information about another angle, beta. We're not given the angles alpha and beta, but we're given the cosines of each. Cosine of beta is -3/5. And it doesn't automatically have to be, but in this case it also turns out that beta is between pi over 2 and pi. Alpha and beta don't have to be in the same quadrant for this. Okay, I want to find two things. I want to find let's see, what do I want to find here? I want to find the sine of, say, alpha minus beta. Yeah, that'll work. And what else? Let's see. I want to find the sine of alpha minus beta and the tangent of alpha plus beta. Okay, so right away we see that we're going to need another formula because we have a formula for sine of alpha minus beta, but we don't have one for the tangent of alpha plus beta. Okay, so we'll cross that bridge when we get to it. Let's do the sine of alpha minus beta first. Okay. Well, let's check out the sine of alpha minus beta. The formula, the identity for the sine of alpha minus beta. Remember, the pattern is sine, cosine, cosine, sine, alpha, beta, alpha, beta. These quantities are multiplied, and we keep the sign. Okay, well, let's plug in what we know. We don't know the sine of alpha, but we do know the cosine of beta. That's -3/5. We do know the cosine of alpha, so that's 5/13. And let's see, cosine of alpha. And we don't know the sine of beta. Okay, so we have some missing pieces of information. So what are we going to do? Well, we got to find those pieces of information. This part of the problem should be familiar to us. This is an old problem for us. Now, what I'm going to do, let me see if I can do this. I want to move things over. Give me just a second here. I'll move this over here a little bit. I'm trying to be efficient with the room on this Surface Pro here. And then I'm going to copy the whole stuff and move it over. Scoot it way over. Okay. I'm trying to make a room on the right hand side here. Okay, so we're given some information about two separate angles, and we need some more information about those angles. So draw them. Let's draw the angles separately. Let me also scoot a little more room in here. Good. More room will be nice. Okay, maybe some in here. Okay. Wish I could do this in the classroom. Okay, so let's draw the angles. We have two separate angles. We have the angles alpha and beta, so we're going to draw them separately. There we are. So the angle alpha The angle alpha is between pi over 2 and pi. The angle alpha is between pi over 2 and pi, and the cosine's 5/13. So I'm going to draw the angle alpha. I'm going to draw it better. Oops. Oh dear. Okay. Here. That's all right. Well, I'm just discovering that the cosine of alpha would be impossible to be 5/13. Okay, so I'm gonna fix things a little bit. The cosine of alpha I want to be negative 5/13. I'm sorry about that, students. The cosine of alpha has to be negative 5/13 because the angle alpha is in quadrant 2. Okay, so we're okay. This is an easy fix. So let's draw the angle alpha, and the cosine is negative 5/13. So I'm putting in this, as I would do in section 2.4, I'm putting in the x value of negative 5 and 13 for the hypotenuse. The Pythagorean theorem is going to leave 12 for the vertical side. Okay, so if you want to go ahead and do the Pythagorean theorem on that separately, that would be fine. Now I'm going to draw the angle beta also, but it's a separate angle, so I'm going to draw it in its position in the second xy plane. So negative 3/5. So here's beta. Negative 3/5. Negative 3/5. And what does the Pythagorean theorem tell us the vertical side is, or the y value is? Should be 4. It's 3, 4, 5 virtual triangle formula formed there. All right, so back to our problem. Back to the problem at hand. We are looking at a quantity that's missing for two things. It's missing the sine of alpha. Well, pick the sine of alpha right off the diagram. The sine of alpha is 12/13. The sine of alpha right off our diagram is opposite, if you will, over hypotenuse. 12/13. 12/13. The sine of beta is 4/5 from the second drawing. The sine of beta is 4/5. Sine of beta. Okay. And then perform the arithmetic. All we have to do is complete the value of this thing. So positive 12 times negative 3 is negative 36, and this is over 65. So negative 36 over 65. And minus 5 times 4 is 20 over 65. And negative 36, take away 20 more, is negative 56 over 65. Okay, so that's the value of the sine of alpha minus beta. Now we have a problem. We have a little bit of a problem. We'll get around the problem very, very easily. Our problem is that the second thing we want to find, the tangent of alpha minus beta, needs a formula. We need a formula. Okay, so let's take a look at the last two formulas for our video segment. We have formulas that deal with the tangent of sums of angles and differences of angles. So remember how I said that trig functions don't distribute with addition or subtraction. In fact, most functions don't. So if they did, we'd have tangent of alpha. Let me rewrite it here a little better. We would have the tangent of alpha plus the tangent of beta. So this is not right. This is not correct. But the formula for the tangent of alpha plus beta starts out with this common mistake. So you can start out with distributing the tangent of alpha plus tangent beta. But then we have to divide by something. Then we divide by 1 minus, and then multiply tangent of alpha times tangent of beta. So the pattern's not so bad, because it starts out the way in a dream world we would like to have the tangent of alpha plus beta work out? And the same thing for the tangent of alpha minus beta. And tangent of alpha minus beta starts out like you'd like it to. Tangent of alpha minus tangent of beta. However, we end up also having to divide by 1 plus the tangent of alpha times the tangent of beta. So the signs in the numerator and denominator are different. And there are our two formulas for the sums and differences of the tangents of sums and differences of angles. Let's finish up our problem. We're looking at the tangent of alpha minus beta, the tangent of alpha minus beta. Okay, so let's do that. So here we go. The tangent of alpha minus beta. The formula is right above us. It's tangent of alpha minus tangent of beta divided by 1 plus the tangent of alpha times the tangent of beta. Okay. Now I'm going to see if I can move our angles down where we can work with them. Let's see. Give me a second here. I just want them next. I just want them nearby. So here. A little too far away. Where are you? There it is. That works. Got them right next to our work. Okay, so there are our angles again, alpha and beta, the same angles. So let's compute this. The tangent of alpha, look at the angle alpha. The tangent of alpha is 12 over negative 5, or negative 12 fifths, minus the tangent of beta is 4 over negative 3, so minus 4 thirds, all over 1, plus the tangent of alpha, 12 over negative 12 over 5, times the tangent of beta, negative 4 over 3. Okay, it's a messy little number, but it's just a number nonetheless. So let's compute this number, and then we'll be done with our video segment. So let's do this arithmetic. In the numerator, the least common denominator is 15. The least common denominator is 15. So if I multiplied negative 12 fifths by 3 over 3, so I have the same denominator of 15, I'm going to get negative 36 over 15. And if I multiply negative 4 thirds times 5 over 5, I'm going to get minus 20 over 15. So now we have the same denominator. And in the denominator, I notice I can do some cross cancellation. 3 divides into itself once. 12 goes 4 times. So it's 1, and multiplying two negatives gives a positive, so 1 plus 16 over 5. Okay, so let's keep moving on this. So this is negative, in the numerator I'm subtracting a negative, so it's like adding negative 36 plus 20 over 15. So remember, 2 minuses, when you subtract a negative, it amounts to addition. So negative 36 plus 20 is negative 16 over 15 over 1 plus 16 fifths. Well, we can make that little 1 right there into 5 over 5. So we get 21 over 5. And we're going to invert and multiply to drive this home. 5 over 21. Maybe draw a little cross cancellation. 5 divides into itself once, into 15 3 times. I don't think anything else, any other kind of cross cancellation can occur. So we end up with negative 16 over 63, I believe, if that's right. Yeah. Okay. And that's the value of the tangent of alpha minus beta. So there's our introduction to the formulas for the sums and differences, trig functions involving sums and differences. We have formulas for sine, for cosine, and for tangent. And with that, I invite you to go dig in homework in section 3.4 as soon as you can. Homework for the section 3.5 promises to be kind of involved, so I'd like you to get through as much of 3.4 as you can before that. So go ahead and get started right away. And as usual, I'm looking forward to talking with you all again very soon.